Okay guys, so let's continue our discussion on a limit state condition. So before we proceed with the allowable stress design, which has, again, this is a strength limit state, uh, we look into the serviceability limit state aspect of your design, and you will notice that the serviceability limit states is very straightforward, wherein your limiting value are simply computed on the basis of the L over R, or the length versus the radius of gyration ratio. Of course, sometimes we have to put a K factor here for the effective length factor uh, to modify, okay, your effective length. And this serviceability limit state condition is applicable for tie rods or tension rods, cables, and the like, okay, which is actually more concerned only on vibration problems and deflection problems. Okay, so the limit must always be less than or equal to 300. So only an additional note here for tension members are provided, no? So again, this is still a part of your LRFD, wherein the resistance measured is a function of your rupture strength. Okay, so this is actually your uh, fracture. Okay, and this 75 is a reduction factor on the area. Okay, so tension rods are actually those which are used to stabilize the elements which can actually twist and sag, like that of the parlin, no? So parlin applicable on parlin design. Okay, so this is an exception for tension rod. So to proceed with the allowable stress design, the limit state criteria is a little bit different. So instead of having a reduction factor and an overload factor, you have here what you call a factor of safety, you know? So Tn all over omega is greater or equal to T, or what you see in our previous discussion, that Rn over omega is greater or equal to Ra. Okay, so this is the criteria, which is basically the same, only a change of variable was made. So two limiting state of strength is used. There's no block shear failure mode here in ASD. So what we do is the yielding of the cross section away from the connection and the fracture of the effective net area of connection. Okay, so the formula is in terms of stress, because this is an allowable stress design. We divide it by Ag, we divide that by Ag, and then compare. Okay, so we divide this by Ag, divide this by Ag, and then compare. So rewriting it, we have the Fa less than or equal to F allowable. So this FA less than or equal to F allowed growth. Meaning to say that the actual stress must always be less than or equal to the allowable stress. That's why this is called the allowable stress design. So it's coming from the fact that all allowable stresses are the ones measured in such a methodology. Okay, so your F allowable now becomes Tn over omega Ag, and if we compute for Tn, this is the force is equal to Fyag divided by 1.67, so all over Ag is 0.60 Fy. Okay, so take a look. This 0.60 is not the von Mises, no? Not the von Mises factor, because exactly the von Mises is 0.577. The 0.6, the other 0.60 that we're using is for shear, and this is not for shear, it's for tension. So I just like to take note on that. So for the fracture of the effective net area of the connection, the procedure is the same, but the factor of safety was increased to 2, since we are talking here of connection. We increase your factor of safety to 2. Okay, it must be bigger. Why bigger factor of safety? Because connections are more critical. Therefore, the design must be more conservative. Okay, so doing the same, the only difference will be your coefficient becomes 1/2 or 0.50. Okay, so that's as easy as comparing your actual stress, tensile stress, with the allowable tensile stress. Okay, so again, no black shear mode in ASD. So this is the formula that we're going to use for the allowable stress design. Okay, for the evaluation of the net area, a procedure must be defined by the AISC, or as defined by the AISC is hereby presented. So if a hole is drilled or punched, it must always be 1/16 inch or 1.6 millimeter greater than the design bolt diameter, which serves as an allowance for bolt insertion. So we cannot drill a hole which is exactly the same as that the diameter of the bolt, because we will be encountering problems of insertion. So hole drilling or punching causes some damages on the perimeter of the hole. So there is now an additional error due to the damage or in punching or drilling, equivalent to 1/32 inch or 0.8 millimeter around. So if we make use of two sides, okay, so this is now the error. So this is now your error due to punching. If the error is 132, and I want to get the diameter of the hole minus the error, so I just subtract 2 times 1/32. So I have here a correction factor again of what? Of 1/32. Okay, so I have here a correction factor, both sides, of 1/32 here and 1/32 there. So if I add it, these two will become 1/16 inch. Okay, so this 116 inch and 116 on the allowance will add up. Okay, so this is the error plus 116 allowance. Your total, okay, your total deduction will be 1 over 8. Okay, so this is 1/8 inch to be deducted to the, not deducted, to be added, okay, to be added to the bolt diameter. So in short, your phi hole is phi plus 1/8 inch, or your phi hole is phi plus 3.2 millimeter, where phi h is the design diameter of the hole or hole diameter, and here's the bolt diameter. Okay, so this is inches, this is in millimeter. Now, what makes the evaluation of net area a little bit more complicated is because of staggering. So what is now a staggered bolted connection? So then staggered bolted connection is a pattern in which the holes are not placed what along a gauge line which is straight. Okay, so an example of a staggered connection is this one. Now, for the net area of a bolted connection uh, which is staggered, the computation will be a little bit different. Okay, so the net area of the bolted connection will be maximized if the bolts are arranged in a single line, but due to a limited length of the connection, the option is to add another bolt line as shown in figure A. Okay, and if the width of the connection is controlled by the width of the plate or the member uh, is also small, then an offset distance, also known as the stagger, may be considered. So another reason for staggering the connection is due to the geometry of the connection as shown below. Okay, so this is one reason of staggering the connection, because the width of the connection is not enough, or another reason is because of the geometry, which is a skewed geometry like this, so your staggering becomes a little bit skewed like this. So in figure C here, which is actually almost similar to this figure A here, the distance S is provided for, and it must be small enough that the influence of an offset hole may be felt by a nearby cross section within the vicinity, such as a fracture along a path ABCD may occur. Okay, so what does that mean? No? So in cases wherein we cannot place a hole directly aligned to this, because your G is very small and we want to avoid uh, a fracture straight along this line, then we move the succeeding hole staggered at a certain distance. But it must be small enough so that the fracture path, okay, along, let's say we now look into this path, the fracture path along this line will only be felt by the hole here. Okay, so it will go here before exiting at point B. Okay, so how do you know, how do you solve for this distance S? So we have a formula to account for that. And doing so will give a stronger or a bigger equivalent net width that will increase the capacity of your connection. Okay. So to illustrate on that, we will be talking of some formula here. So in such a case, the relationship for simple stress will no longer be valid, since the failure involves both tension and shear stresses. Hence, to account for this, which is proposed by Cochrane 1922, suggested the use of a reduced diameter of the hole to account for the increase in strength due to shear. So staggering is just like reducing the diameter of the hole. Uh, it is reducing the diameter of the hole or simply increasing the strength due to shear. So it's an analogy between the increase in strength and the reduction in diameter. When the hole is big, then the net area will be small. So when the hole is reduced, the diameter is reduced, the net area will be big. Hence, d prime is equal to d minus s squared over 4g, where this particular expression here is actually what you call the effect of the stagger. And the effect of the stagger is beneficial to the connection. Okay, so the net width of the plate in figure C will then be net width is equal to the gross width minus summation d prime. So in this case, this is your figure C. Look. Okay, so the net width is simply the gross width here. This is your gross width, WG, and the net width is simply equivalent to WG minus the reduced diameter of the hole, which is summation d prime. Okay, so that is how the formula was derived from this. And of course, we know d prime is given by this formula. We just plug it there. This becomes what? Algebra. So this will be distributed. Therefore, Wn is now equal to Wg minus summation d plus summation s squared over 4g, where Wn, Wg, s, and g are the net width, gross width, stagger distance, and the gauge distance. Okay, so we will be looking at these equations on the next video by solving one of example here in this lecture. For now, I'd like to end this video and see you in the next video. Thank you very much.